Okay, so this is going to be a complement video to chapter 1, specifically sections 1.7, I believe, through 1.9. So let's work right through this. So at first, we're talking about how single bonds are formed in organic compounds. And it shows us this picture here of methane. So believe it or not, chapter 1 is the first chapter where you can start using your model kit, which is pretty exciting. So I've built methane here. So you could see the same thing here as is right above it. Okay. Now, the interesting thing is, and what it says here is that a bond protruding out of the plane of paper, there's one towards the viewer, which is a solid wedge. There's one projecting back from the plane of paper away from the viewer, which is a hatched wedge. And then there's two others that are in plane of the paper that they should always be drawn adjacent to each other. So what this means, and if you hold methane, which is a tetrahedral in terms of its geometry, the best way that you can do this, there's not going to be one directly going this way towards you and directly away from you. That would be 180 degrees, which we're not going to find in this, but you are going to have one that you can look straight ahead at. All right, in my case, it's going to be this one. So this is, I'm looking directly down the sights of it, okay? Now, I can hold on either side these two, and I can see that these two are they're in the same plane, all right? They're in plane with each other. If I rotate this, they are in the same plane, okay? And that I'm going to make these two, okay? Now, this is coming towards me, so this would be the solid wedge. This would be coming out of the plane of paper toward the viewer. The one that's going away from me is this one here. This would be that hatched wedge, all right? So that hatched wedge is this here. So this is a little sneak preview to, chapter 4, which you will learn all about how to use these and how to look at molecules and compounds and atoms in 3D space, okay? All right, let's move on here. So again, bonds in the plane of the paper must be adjacent to each other when you're drawing what's called these perspective formulas. All right. Then it asks, you might be wondering how carbon can form 4 covalent bonds when it has only 2 unpaired valence electrons. So this methane has 4 covalent bonds. It's carbon in the middle, and it's attached to 4 hydrogen atoms. This is methane. All right. And this is a good question, because when we think about that chromium and copper exception, where we borrowed an electron from an s orbital and we put it into, I believe, a d orbital, we can see that we can kind of do the same thing here. This is the electron configuration for carbon. So 1, 2, 3, 4, 5. We have 6 total electrons. And we have 4 valence electrons. So that's true. We have 4 valence electrons, but one set is already paired in our 2s orbital here. So what we can do, and actually what does end up happening, is we do take 1 electron out of 2s and we put it in this 2pz orbital, or just the third of the 2p subshell. So that is exactly what we do when we prepare carbon. I don't know if that's what happens when carbon bonds with hydrogen, but it's definitely what's going to happen when carbon bonds with actually, you know what? That is exactly what happens when carbon bonds with hydrogen, because this is methane right here. So let's walk through that. Okay. So enter hybrid orbitals. What we see over on the left is also what we see on the right here. In our it doesn't say 2s, but this is the 2s orbital, and there's 2 electrons. And these are our p orbitals, and we have 2 electrons, and this one's empty. So yeah, we are going to pull an s electron and put it into our p electron. It's called promotion. We're going to put it into our p orbital. It's called promotion. So now we still have 4 valence electrons, but now each of these orbitals has 1 electron, okay? Now we're not going to stop there. We're actually going to take this one additional step, okay? We're going to hybridize these, and this is what this means. So we have 1 S and we have 3 Ps. We're literally going to put them into a blender or mix them into a cup. We're going to shake it up, or we're going to blend it up. So what is, and then we have a single mixture, right? Well, what is that mixture? Well, it's 1 part S. We put in 1 part S, and it's 3 parts P. That's what is making up this mixture. So it's 25% S character and it's 75% P character. What we're going to do is we still want to distribute 4 electrons. So we're going to, into 4 cups, empty this solution into each of the 4 cups. All right. We're going to call that new solution, which in this case is actually a new orbital that we're creating. We're calling that the Sp3 orbital. So what I was just saying, this is what we have right here. These are those 4 new glasses that we're filling up. They're the same energy level as each other, but they're a slightly lower energy level than a p orbital, which we know is a higher energy level than an s orbital, okay? So, and we're going to call these sp3 because it is 1 part s and it is 3 parts p, okay? So that is what we're doing here. So carbon now, before it even bonds into anything, is going to look, well, let's not jump ahead. All right. And this is kind of how this looks like from a graphical perspective when we're actually looking at these orbitals. This is that s orbital. These are the 3p orbitals. When we mix them all together, we're going to make these really cool looking like orange goblets here. These are our 4 new beverages, our 4 new orbitals. They're called sp3. So carbon, if I just take a carbon atom here, we're going to pretend that it has sticking out at these 109.5 degree angles, these sp3 hybridized orbitals, each one of those holding 1 electron. All right. If we want to visualize that in a certain way, it's going to kind of look like this. Each stick here is not a bond in this case, it's just 1 electron. So we have our carbon atom in the middle with its 2 non-valence electrons, just it's the inner, the first inner ring, the 1s2 of carbon are going to be inside of there. And then 2, and then 3, 4, 5, 6. So 6 electrons, which of course makes up carbon. Yes, I had to make sure I had that right. So yeah, so this is carbon. Now in this tetrahedral formation, which it already was kind of tetrahedral, but they are sp3 hybridized orbitals. They are the same energy level. Each one has 1 electron within it somewhere. It is ready to go. It is ready to bond. It is ready to bond with nature. All right. Now, does this have a specific charge? Well, it has 6 protons and it has 6 electrons. It doesn't really matter how many valence electrons it has in terms of a charge. So no, this is neutral charge. Does it have a full octet? Well, no, it doesn't, because it has 4 valence electrons and we want 8 valence electrons. We have space for 8 of them. 1, 2, 3, 4, 5, 6, 7, and 8. So, but each one of our sp3 hybridized orbitals just has 1 electron. So they have room for 1 additional electron each, or 4 additional electrons. As a carbon atom, we can bring in 4 additional electrons, which makes carbon so powerful. That's why it can make 4 covalent bonds. It's ready to share, okay? So what happens is, Then you have a hydrogen that comes along. And we can see that with this green circle here, a hydrogen is going to come along. And a hydrogen is nothing but a proton, which by itself, which is be an H plus, and an electron, right? A neutral hydrogen atom is just a proton and an electron kind of ready to go, right? So that is going to come and it's going to attach with one electron to one side of the carbons, all right? So now this is a single covalent bond, and this is what occurs when an sp3 hybridized orbital overlaps with just a normal s orbital. A hydrogen just has an s orbital. It has one electron. It's ready to bond with something. So it's going to share that one electron with the carbon sp3 orbital that had one electron also. So two electrons between there, okay? And that's just going to happen 3 other times. We're going to bring hydrogen here, and we're going to bring a hydrogen here, and we're going to bring a hydrogen here. So now we have a tetrahedral methane atom. This is CH4. It's neutral. Carbon still has 6, well, it had 6 protons, 6 electrons before, but now it has 8 valence electrons because it's sharing via that covalent bond. It's now sharing electrons with hydrogen, okay? So you have 1, 2, 3, 4, 5, 6, 7, 8. Now each one of these actual sticks, each one of these actual bonds has 2 electrons. So this is a full octet. This is an incredibly stable, happy molecule of methane, all right? Again, tetrahedral, each angle here is 109.5. So you can see it's a little bit bigger, a little more obtuse than a 90-degree angle. That's where that 109.5 comes into play. And the other thing is, the reason it's shaped like this is because electrons repel each other. So there's still these orbitals here where these electrons are kind of sitting, and electrons repel each other. So they want to get as far as possible. And mathematically, this is, you know, a tetrahedron, this is as far away as they can get. You know, if this, for example, was like here, that's too close. You know, it wants to get as far away from this and this and this as possible. So that's what is going to put it there. Okay. All right. So now let's expand this a little bit and let's get into ethane. So ethane is 2 carbons and 6 hydrogens. And it's going to look like this. So it has 2 carbons, and it has, each carbon is attached to 3 hydrogens, and each carbon still has a full octet. Look, if I pull this off, and we're going to say that that's 2 electrons, 2 electrons, 2 electrons. It still has a full octet, especially when it is sharing that middle electron with another carbon. So again, a very stable molecule. And what happens is kind of exactly the same. You have a carbon that is sp3 hybridized in all 4 of its, we'll say, electron domains, and another one that is sp3 hybridized. But instead of bonding with a hydrogen, they're going to bond with each other, and they're going to connect, and they're going to look like this. So this is an sp3 hybridized overlap that is bonding this. This is an sp3 and S, which we could see in those green circles here, bond that is going to form those single bonds. All right, so still single bonds. They are still sigma bonds. All single bonds are called sigma bonds, but the orbital overlap that is causing those bonds are different. Just keep that in mind, okay? All right, and you can also keep in mind these 2 carbon atoms are always in plane, right? I'm not bending that any specific way. So we're still fitting that tetrahedron, but the carbon atoms you can see they're kind of locked in plane there. I mean, they can kind of rotate here, but they're always going to be one in front of the other. Okay. And yeah, so I said here, it might be tempting to think that two sp3 orbitals, because here we're just overlapping an sp3 and an s, and it might be tempting to think, well, an sp3 and an sp3 overlapping is going to kind of do something special. It's not. It's just going to form another sigma bond. All right. So I'm saying here we have 14 valence electrons that we can see, 6 protons in our hydrogen atoms and 6 protons each in our carbon atoms. So 18 protons and 14 valence electrons. Don't forget that the carbons each have 2 electrons in their first shell, that 1s2. In the 1s orbital, that's why this is a neutral molecule. Okay, let's continue here. Yeah, so you'll quickly learn to identify that an sp3, you can call this an sp3 carbon because it is, well, it's sp3 hybridized on all of its electron domains, right? It has 4 sp3 orbitals, but it's also attached. It has 4 bonds, 4 separate bonds, and you just subtract 1. So if it's attached to 4 things, it's an sp3. You can think, well, it's attached to 4 things, but to make that, I had to take 1 s and 3 p's. I had to take 4 ingredients to then make those 4 sp3 orbitals, right? So there's 4 sp3 orbitals, but it's s, and it's 3 parts p. So I don't know, you can kind of think about that. All right. From this kind of wonky type of orbital thing, this is how sp3 orbitals kind of come together. You're still going to have that sigma bonding molecular orbital and that sigma anti-bonding molecular orbital. But let's talk about how a double bond is formed. All right. And we're going to talk about the bonds in ethene or ethylene, which looks like this. So this is ethylene. We can see this double bond here. The really cool thing about ethylene is that the entire molecule is in one single plane. If I do this, everything eclipses on itself. You can't really even see the molecule behind anymore. So that is going to be the really important, interesting thing about this. This is what's called what is it called? Well, there's 120 degrees of geometry here. I believe it's technically called, a trigonal, it's technically called a trigonal planar in terms of the molecular geometry. All right, so what we're going to do here is carbon itself, the carbon itself only needs to trying to think of the best way to explain this. It only needs to attach to 3 things. It is going to attach to 2 hydrogens. So it's going to sp3 here, and it's going to sp3 here, and it's going to attach to 1 carbon. So essentially, it really at first just needs that 1 sp3 bond between the carbon and the carbon. So we have an sp3 and sp3 and an sp3. But what's going to be different this time is that we only need, rather than 4 domains to make those sigma bonds, we only need 3 of them. So we're still going to start with our initial electron configuration of carbon that has been promoted. We're just not showing the promotion in this step. So we are taking our promotion here, which is all the way back here. So 1 in the S, 1 in each of the 3 Ps, and we're only going to use 3 total. We're going to take 1 S and 2 Ps. We're going to blend them up. 1 part S, 2 parts P. So it's going to be called sp2. Now, it looks by itself, it looks exactly the same, okay? But the geometry is going to be a little bit different, right? So we're putting three things into a blender, we're spitting them out, and now we're making a new orbital called sp2, and we're going to make three of them because we're preparing to connect to three other things. But this time, we're leaving something out. We're not using all four ingredients. We're leaving an unhybridized p orbital just on its own. And if you remember from way back when, a p orbital is that kind of doorknob shaped, well, this is them right here in the purple, it's that kind of doorknob shaped molecular orbital. So we're leaving one of those by itself, and we're going to see that we're going to end up using that, right? So this here is our sp2 hybridized carbon, and it's going to look like those are not going to be on the same plane. Well, I don't know that I can actually make a model of that itself. We need like 5 things. So we can't really make a model of that at the moment, but we'll keep going and I'll kind of show you what's happening here. All right. So we do that original thing. We make these now sp2 hybridized orbitals. And we end up with a carbon that looks like this. So we're going to have a carbon. We're going to have a carbon that theoretically has on the same plane 3 sp2 hybridized orbitals, one going this way at 120 degrees, one going this way at 120 degrees, one going this way at 120 degrees. And then going vertically like this is going to be that unhybridized p orbital, okay? So we still have 4 orbitals that we're working with, but 3 are that sp2 hybridized, and 1 is that unhybridized doorknob p. That unhybridized doorknob p is in the purple here. These sp2 are that new ingredient that we created from 1 part s and 2 parts p. So we could say that this is 66% p character and 33% s character, okay? Now, when we bring these together, when we are bringing this bottom left A here, I can show you this. We're going to say this is my carbon with 2 hydrogens. So this is what you see on the left. And this is my other carbon with 2 hydrogens. And this stick, we're going to say, is our sp2 hybridized orbital. All right. So these sp2 hybridized orbitals are going to overlap, and then they're going to form a bond. Okay. In this case, I'm just using a longer stick. So this is going to be like our inner rim result. Okay. Now, it looks kind of similar to methane. Ethane, but we're going to make a double bond. We're going to do something different because, yes, we've brought these together, but this is kind of in separate pieces. These purple p orbitals still exist. So yeah, this is connected, but we have a p orbital here and a p orbital here. We have these really strong, high-powered p orbitals here, and what they're going to do is actually like overlap with themselves. So there's like a node up here and a node at the bottom, and they're going to like overlap with themselves and like wrap around like saran wrap. So these purple things would be my fingers that I was just showing you. And we're going to like, imagine somebody wrapping my pointer fingers together. And then if I have my thumbs down here, imagine somebody wrapping my thumbs together. So we're mashing them together. The final product of what this looks like is on the right here. The linking together of both nodes of a p orbital, unhybridized, That is called a pi bond. That is a double bond in organic chemistry. Okay. What this looks like here, as those p orbitals are pulling this molecule together, it pulls everything. See how this is in a different, how these are in a different plane? I can like rotate this, and you know, these are angled out. This double bond pulls everything into a single plane. You really have to make this with the model to be able to see it. It's really kind of cool. So now everything is in one just flat kind of plane here. All right. This is ethene or ethylene. All right. It's named ENE because it is an alkene. We'll learn about that a little bit later. But this is our final product here. Now, we need to remember it's a double bond. One of these is a sigma bond that was made with the overlap of two sp2 hybridized orbitals. The other one, it doesn't really matter which, the other one is a pi bond that has been formed by two overlapping unhybridized p orbitals. And that p orbital, it's this one here. It's that unhybridized p orbital that from the beginning, we never touched. We didn't mix that together. We kept that the same, that doorknob p orbital, okay? All right. Now, don't forget, because I'm wrapping around my fingers on this side, the one node of these p orbitals, and I'm wrapping around my thumbs on you know, or my thumbs underneath or whatever, but it's only making a single pi bond. You're like, well, how can this be? I'm bonding two things together. Well, remember that there's only one electron in this p orbital. So that's the one thing we have to keep in mind, that we're bringing a p orbital and a p orbital together with two nodes, this p orbital together, but they only are holding one electron because our p orbital, and we're bringing two carbons together, but our p orbital, it only has one electron in there. So if we go back to like way back to that original, to this thing, we're still making, I believe, a bonding molecular orbital and an anti-bonding molecular orbital. We're putting both of those electrons into the bonding molecular orbital. So even though we're connecting two different things, one is facilitating that bonding and the one really isn't facilitating that bonding. So I'm pretty sure that's the reason behind that. That's kind of why that happens. All right. All right. So the last thing we need to get through here . So I kind of have that explained. The last thing we need to do here is with ethyne, all right? And this is with a triple bond. So we're going to do the same exact thing. We're going to prepare carbon, but this time to only make a connection to two other things, not three other things. So we only need two ingredients this time. We're going to go back to our same standard promoted carbon electronic configuration. In this case, it's going to be 2s1, 2p, 2p3 or 2px1, 2py1, 2pz1. But we're just going to take one part S, one part P. So it's going to have 50% S characteristic and 50% P characteristic. Put them in a blender, mix them up, pour them into two new orbitals, which is going to be one part S, one part P. So we're just going to call it SP, but we're going to keep two p orbitals unhybridized, okay? So when we bring this molecule together, we have a carbon on this side. Now, there's two sp hybrid orbitals. One is going to be joined by a hydrogen, and the other sp orbital is going to overlap and form that sigma bond and going to bring those carbons together. And that's exactly what we see here. However, now we have two. So now we have like two sets of doorknobs coming together, and this actually looks like a clover. So we're actually saran wrapping 4 different things, but we're still only making we're 2 additional bonds here. So we're bringing an unhybridized P and an unhybridized P, 1 sigma bond, 1 pi bond, and 1 unhybridized P and another unhybridized P orbital, putting them together, making that 3rd pi bond. All right, so we're going to connect 2 P's right now. So this is our first sigma bond created by sp orbital overlap. Now we're going to overlap the orbitals of our first unhybridized P orbital, and that's going to do that. So kind of similar to what we were just seeing with ethene, but now for a 3rd time, we're going to take that last unhybridized P orbital, overlap it with the other unhybridized P orbital on the other carbon atom, and make a 3rd bond, but a 2nd pi bond. This is going to create, which we can see in the ball and stick model here, something called ethyne. This is a linear molecule. It's just a line. It all disappears if you look at it this way. It's just a line. So this is ethyne, this is ethene, and this is ethane. All right, I think that's pretty cool. So this, anything you put off of this initially is just going to be in a straight line. It's like a dumbbell or something. This, and this is actually like a quiz question, you can see everything here is in a single plane. All right, even if I take off a hydrogen and I throw on a carbon to this molecule, it's still all in the same plane. Anything attached to what's called an sp2 hybridized carbon is going to be within the same plane as that sp2 hybridized carbon. This, and this. They're always going to be in the same plane, all right? This is sp2 because it's attached to 3 other things, 1 here, 1 here, and 1 here. And we made that by creating those sp2 hybridized orbitals, right? But if we continue, now that we're attaching something to not an sp2 hybridized carbon to an sp3 hybridized carbon, well, that's going to be able to rotate. That's going to be the first thing that is going to be allowed, this hydrogen atom. It's going to be the first thing that's going to be allowed to be out of plane. So again, the model is just a really great way to get a grasp around the geometry, because it all really does make sense. When you're holding it in your hand, how easy to answer a geometry question when you can actually build what you see on the screen and just rotate it around. So that's it. Hopefully that makes these 3 sections a little bit easier to understand.